Hi, good morning, everyone. Welcome back to the second set of talks for today morning's very interesting seminars that are going to happen. I am Prasad. I work at the Indian Institute of Science, Education and Research, Mohali. I also am the secretary of the Indian Society of Evolutionary Biologists. We are very happy to be co-hosting this special set of talks along with SSE. A big thanks to all the people who are involved, especially people from the SSE and all the others who are supporting this program in the background. With that, let me get straight to the talks of this session. I would like to introduce Aritra Biswas. Aritra is a PhD candidate at the Center for Ecological Sciences, Institute of Science. He studies the historical biogeography and macroevolution of tarantulas. Broadly, he's interested in the processes that generate and maintain biological diversity over large timescales at both global and local levels. Today, he will speak about how Clade age and urticating hair explain the patterns of diversification. Aritra, you please remember that you can.
Sorry, I can't hear you. I mean, the last part.
Aritra?
Yeah.
Yeah.
So I'll share my screen. I hope everyone can see my presentation and also hear me. All right. Am I audible?
Yeah, Aritra, we can see your presentation.
Okay. Then I'll go ahead. Yeah. So hello, everyone. The title of my presentation is that Clade age and urticating hair explain the patterns of diversification in tarantulas. And this work is a part of my second chapter of my PhD thesis. And here I have used tarantulas as a model system to address a very fundamental question in ecology and evolution. That is, the tree of life is extremely asymmetrical in terms of species richness or diversity. So some clades we see which are really big and has more diversity, whereas the other clades has very less diversity. So in this phylogeny of reptiles, you can see that in case of squamates and other snakes, they have around 11,000 species, whereas birds has around 11,000 species. Whereas crocodilians, they have only 28 species. And you can see the stark difference in the diversity. And also in the mammalian phylogeny, where the species richness is shown, you can see that the order Rodentia is an outlier. It has more than 2,000 species, whereas Chiroptera, that is bats, has more than 1,000 species, and the other clades, the other orders, they don't even come close to this too. And why is that? And also, this is a phylogeny of tarantulas. So there are 13 subfamilies for tarantulas, and here you can see that there's a subfamily level phylogeny. That phylogeny of tarantula is no different than others. There is this group Theraposinae, which contains more than 50% of the extant diversity. Then there are groups like Selenocosminae with more than 100 species, but there are groups like Sphygmopoinae, Stromatopelminae, which are extremely species poor. And why is that? So to date, there are like two broad categories of explanation that why do we see such asymmetry in diversity. So the first one is the Clade age hypothesis, which assumes a correlation between the crown group age of the clade and the species richness. So according to this explanation, the bigger clades, which are more diversity, they're older. So simply they had more diversity, more time to accumulate more diversity. So in this diagram, you can see that this clade is older. It started diversifying earlier. So that's why it has more diversity than this clade, which started diversifying later, and this is small. On the other hand, the other class of explanation is the diversification rate variation, which suggests that the bigger clades, which are more diversity, so they have more diversity due to higher net diversification rate. And the net diversification rate is given by speciation rate minus extinction rate. And these two rates can get affected by a number of biotic and abiotic and other biological or ecological factors. So if a clade has more diversity, then it can be either due to elevated speciation rate or due to lowered extinction rate. So these are broad categories of explanation. There are other classes of explanation, right? Age rate scaling, but those have been shown to be artifact of sampling. And to date, studies have shown so here in this case, you can see that this clade is smaller. It started diversifying later, but still it is bigger because it has higher net diversification rate. Whereas this clade is older, but it has lower net diversification rate. So it is smaller. So to date, studies have generated mixed support for both the scenarios. So a landmark meta-analysis by McPeak and Brown has shown that where they have investigated 6,000 taxa, and they show that mostly it is clade age and not diversification rate variation that explains the distribution of diversity. On the other hand, another study by Rebusque et al. Has shown that with 54,000 taxa, that mostly it is diversification rate variation and clade age and species richness are decoupled across the eukaryotic tree of life. And several studies have shown that different abiotic as well as biotic factors can affect the speciation and extinction rate, creating these patterns. Another important study by Bloom et al. Has shown that these two scenarios are not mutually exclusive, and often they together interact to generate different patterns of diversity. Like in case of the family, water beetle family Hydrophilidae, there are 14 subfamilies, and 12 of them can be explained by clade age, and 2 of them can be explained by diversification rate variation. So this is a schematic representation showing how the interaction of clade age and the diversification rate variation can interact to generate different patterns. So if you're testing the correlation between the age of the clade and the species richness of the clade, if there is no significant variation in diversification rates, then we'll find a very strong correlation. On the other hand, if there is variation in some clades, then this pattern will get slightly broken. On the other hand, if there is strong variation in diversification rates, then we'll see that the age of the clade and the species richness correlation is totally decoupled, and there is no pattern at all. So given this background, now I'll give a brief introduction about my model system. That what are tarantulas? In one sentence, we can call them a large, hairy, ancient spiders. And the spider family Thyrophosidae is commonly known as tarantulas. And tarantulas belong to the infraorder Megalomorphae. So overall, Megalomorphae is extremely species poor compared to the other group, Araneomorphae, which contains 95% of the extant spiders. And Megalomorphae are called old spiders. And within Megalomorphae, there is tarantula. And why tarantulas are interesting in terms of ecology and evolutionary studies? Because as a gross, Megalomorphae is a very species poor group. But within Megalomorphae, tarantulas, they represent an outlier. They have more than 1,000 species distributed worldwide. And tarantulas represent like the biggest spider in the world. They are probably the only spider group capable of taking down small vertebrates like snakes and birds. And this Goliath bird eater tarantula is the biggest spider in the world, whereas this small group of tarantulas known as Ichnocolinae from Middle East, they represent one of the smallest group of spiders. So you see this extreme size variation, and also they have a diverse suite of adaptive traits. Like perhaps the most interesting trait about tarantula is urticating hairs. So these are small microscopic hairs which has barbed end and harpoon-like structure. And whenever they feel threatened, these hairs are situated at the back of their abdomen, and they just shoot or flick this hair in the air. And if they come in contact with the skin of the predator, it can cause allergic reaction, skin blistering, then irritation, or temporary or permanent blindness. And all tarantulas are venomous. So they have a combination of neurotoxic and cytotoxic venom, and also they come in all sorts of color. So given this, and tarantulas have been very famous in movies, in ancient folklore, and also as pets throughout the world. So given this background, what could be the potential reason for such asymmetry in case of clade size in tarantulas? So either it can be the clade age, that usually the bigger clades which are more diversity, they are older. On the other hand, it can be microhabitat use. So in tarantulas, we see that either they're on the ground or they're on the tree. And we do see the pattern that the terrestrial tarantulas, they are more specious like Thyrophosinae, Selenocosminae. These big groups, they are all terrestrial. On the other hand, arboreal groups like arboreal subfamilies, they are species poor. Or it can be anti-predatory defense strategy, that is the urticating hair. And urticating hair evolved multiple times only in like South American tarantulas. And there is the escape and radiate hypothesis, which suggests that once you evolve a very effective anti-predatory strategy, it reduces the predation pressure. And when that ecological pressure is not there, then the organisms can remain more exposed. They can explore more niches, and as a result, diversify more. And we do see the pattern that this extremely specious subfamily, Theraphosinae, they have the most diverse and conspicuous kind of urticating hair. So we tested all these hypotheses using a bunch of phylogenetic comparative method. So we used a GenBank mining approach to assemble a global phylogeny of tarantulas with both nuclear and mitochondrial markers. And we got a chronogram of tarantulas using marker-specific substitution rates and also secondary calibrations from already published paper. And then we tested the correlation between the crown group age of the subfamilies and the species richness distribution across the subfamilies. Separately, we employ different trait-independent and trait-dependent diversification tools to test the correlation between presence and absence of traits and the speciation and extinction rates. And also, we performed ancestral state reconstruction to understand the directionality of evolution. So for the results, we performed phylogenetic linear regression to test if how much variation is explained by the crown group age. And here you can see that for all the subfamilies, there is a very strong correlation between the crown group age of the subfamilies and the log transform species richness value. So it is a significant pattern, and clade age explains around 49% of the variation of this asymmetry and diversity. But there are some outliers like this extremely specious subfamily Theraphosinae, and there are some arboreal subfamilies like Poecilotherinae, Stromatopelminae. So then we wanted to test whether these outliers are due to trait-dependent diversification, or is there any variation in diversification rates. So first, we performed ancestral state reconstruction. And what is important here is that in case of microhabitat, terrestriality is the ancestral state and arboreality evolved independently multiple times, at least 5 times. And there is no loss of arboreality. And in case of urticating hair, absence of urticating hair is the ancestral state. And urticating hair evolved independently at least 3 times, only in New World tarantulas. And there is no loss of urticating hair. So then I used the binary state speciation extinction model to test the correlation between the diversification rate and the presence and absence of traits. So in a full Biswas model, we have 6 parameters. So lambda means the speciation rate and mu means the extinction rate. And there are transition rates from state 0 to 1 and 1 to 0. And state 0 means the absence of urtication and 1 means the presence of urtication. In a full model, all these parameters can vary. They are independent of each other. So, and then you can constrain these parameters to be equal between states and come up with n number of other models like in a trait independent model, these parameters should be similar between states. So with permutation combination, you can fit different models. And for the result, we saw that in case of urtication, it is supporting a full model where it is suggesting there is variation in diversification rate between state 0 and 1. And it is suggesting a very low extinction rate in presence of urtication. And the support is very strong for a trait-dependent model. Whereas in case of microhabitat, state 0 means terrestriality and 1 means arboreality. It is still supporting a trait-dependent model, but the support is very low. And in case of Biswas, we are only sampling one trait. So the rate of type 1 error is much higher because we can only have rate variation. What if there is rate variation in the phylogeny or asymmetry that is due to some other trait that we are not sampling? Then Biswas will show false positive hits. So that's why then we have used the hidden state speciation extension model, which is a improvised framework of the Biswas model. And here we have hidden states like state A and B within state 0 and 1. So what Biswas allows to come up with more complicated null models, which can generate the same pattern. And it allows the pattern to be there if it is due to some other traits and not the trait you are sampling. So the rate of type 1 error is much lower. And the results of Biswas in case of urtication is supporting the result of Biswas, that is extremely lowered extinction rate in presence of urtication, and it is supporting a state dependent diversification. It's very strong support. Whereas in case of habitat, it is supporting a null model with very strong support. And this is the phylorate plot estimated with Biswas. So this figure is a bit complicated to understand, but here you can see that there are 2 colors. The external color is red and blue that represents the average net diversification rate, and the internal color is white and black, which represents the trait states. So black means presence of urtication, white means absence of urtication. And you can see that whenever urtication is present, the net diversification rate is much higher, that is 0.11. And whenever urtication is absent, the net diversification rate is much lower. And this is the extinction rate estimated with Hisse. And you can see that whenever it is black, the color is blue. That is, the extinction rate is much lower. It is 0.01. Whereas in case of presence of the urtication, the extinction rate is much lower, much higher. So these are the trait dependent methods, and they have their own limitations. So then I employed the
Aritra,
missing state.
sorry to butt in. You have about 3 minutes.
Oh, okay. Thanks. So then I employed the missing state speciation extension model, which is a trait independent method, and it calculates the lineage specific diversification rates without the trait information. So these are the lineage specific net diversification rate estimated with the missing state speciation extinction model. And you can see that whenever the trait states are mapped separately across the tip of the phylogeny, you can see that whenever urtication is present, the phylogeny is red. That is, the net diversification rate is much higher. And then for the rest of the phylogeny, it is blue. And then we extracted the tip rate separately and tested for correlation between whether the average rates are significantly different between trait states using PGLS ANOVA. And it suggests that in presence of urtication, you can see the net diversification rate is much higher, and it is lower in absence of urtication. And same for extinction rate, just the pattern is inverted. Whenever urticating hair is present, the extinction rate is much lower. And here also in the box plot, you can see the same. And then one can always argue that since South America harbors the more than 70% of the diversity of extant tarantulas, so is it like a range dependent diversification, or whether is the geographic range has any effect on the diversification process? So we employed the geo-Hisse method and tested for is the process of diversification dependent on geographic ranges, but it is supporting a null model. So the landmass of South America does not have any effect on diversification, and probably it is due to the presence of this trait. So to conclude this work, the major findings are that the clade age is a major predictor of disparity in species richness in case of tarantulas at the subfamily level. And looks like the deviation from clade age to species richness relationship, those outliers are due to evolution of urtication. And both trait dependent and independent methods, they identify higher net diversification rate associated with urtication, and the diversification process is range independent. And why urtication is so advantageous? I have already explained that they give direct antipredatory advantage. So whenever the tarantulas can just shoot urticating hair, it buys the tarantula enough time to flee away from the situation. And also they provide indirect benefit, like all tarantulas are venomous, but it has been shown that urticating hair tarantulas have less medically significant venom. So it is plausible to think of a scenario where evolution of urticating hair and tarantulas show two clear divergent strategy of antipredatory defense. Either they bite or they shoot urticating hair. So probably the evolution of urticating hair has caused a loss of venom components, giving them extra advantage, as it has been shown that venom is a costly resource to produce and maintain. And urticating hair is just made of chitin, which is a part of their exoskeleton. So thanks everyone. And this is a video showing a tarantula flicking its urticating hair. You can see the microscopic hairs that they're hardly visible though. But yeah, that's it. Thank you. And if there is any question, I'll be happy to answer.
Yeah, thank you. Absolutely fascinating. Tarantulas are always fascinating, and this makes it even more fascinating.
Yeah.
I would now like to request everyone to please post their questions. You can post it in the question and answer box. Just trying to check to make sure that I'm looking at the right box for the questions. Okay, as we wait for, okay, here is a question. I don't know if you can see the question, Aritra. I will read it out for you.
I can see it.
Yeah, please, if you want to take it.
Urticating hair was convergent or parallel evolution.
If the urticating hair was convergent or parallel evolution, also size and diversification rates, are there any trends?
Well, I don't think so. I have not tested for correlation between size and diversification rates. But if I look at the distribution of sizes, so all these terrestrial and arboreal tarantulas, they're really big, and only the tarantulas like belong to the group Ischnoculinae, they're smaller. And by looking at the species richness distribution, I don't think that there is any trend in the body size and diversification rate. And urticating here, I think it is a convergent evolution which evolved due to predation pressure. Yeah, which evolved multiple
You,
times in only newer
here is the
tarantulas.
second question. Does the time of appearance of urticated hair, early or late, interact with clade age to affect diversification?
Yeah, I think so. This is a very interesting question. So, in case of, if you look at the correlation between clade age and diversity, the species richness, you will see that this bigger subfamily, this Theraphosinae, it is also the oldest. So maybe so it has more diversity being older, and also it has like 3 or 4 different kinds of urticating hair. So I think you are right that clade age and urticating hair, they're interacting with each other to produce this more diversity.
Sorry, Aritra, your last part we couldn't clearly hear. Whatever you said in that.
Yeah, I was saying that this biggest subfamily, which has the most diversity, it is also the older. So the crown group age is like oldest for this subfamily. And also this is the subfamily which has like most diverse kind of urticating hair, like 3 or 4 different types of urticating hair. So I do think that for this subfamily, there is an interaction of clade age and urticating hair that is causing more diversity. So yeah, I think that you are right. They do interact to create like this pattern.
Okay. I think, okay. One more question. Maybe we'll take this question and then move on. There are different types of urticating hairs. I would like to know if the effect of these different hairs is the same. Does it affect in a similar way?
Okay, so for this work, I as across like treated all urticating hair as like the presence of urticating hair. I did not test if the different kind of urticating hairs have different effect. But if you look at the microscopic patterns, there are 7 different kinds of urticating hair, and they do serve different purposes. Like some of them cause skin blistering, some of them cause allergic reactions, some of them cause blindness, and some of them can be integrated into the silk of the tarantula so that it gives passive protection against parasitic wasps or ants. So they do serve different purpose, and I won't be surprised if they affect the diversification process differently, and some of them are more effective against others. But yeah, for now we don't have enough data to. I can only speculate.
Okay. Thank you, Aritra. Thank you very
Yeah.
much for a fascinating talk. I'm sure there are many other questions. If we have missed any, I'm sure to pass it on to Aritra after this talk.